Today's tutorial will be on electronics. We will be discussing a very important segment of electronic termed as analog signal and digital signal first, and then if the time permit us, then we will actually go on to the logic gates and truth tables. Now first let me start with the diagram, because a diagrammatic interpretation is more appealing than the writing part. So here I'll be measuring time, and so this side is our time, and on this axis we have voltage. Okay, and let me make one more. So here again I have time on this axis, so T, and again I'll be having voltage, so that is this way. Okay, and there will be some dotted segment also in this, we will do it later. Okay, so this is 0, and let me now with blue ink I'll be drawing this. So we have something like this. Okay, so let us first define the analog signal. Okay, so analog signal so the very meaning is that a continuous time varying current or you can even say a voltage signal. This is termed as an analog signal. Okay, now this particular graph which I have done with in terms of voltage and time actually represents the analog signal, or it represents more specifically a typical sinusoidal or sinusoidal analog voltage signal. Okay, now what you must know is that the electronic circuit actually which gives out any type of analog signal is called analog. So this is for any type electronic circuit. And let us now learn about digital signals. So before that we need to finish this diagram. So say this is 1.1, this is 5V, 5 voltage, marking it like this, and then let me take, okay, and I'll just draw using the blue ink. It is like this, then again it is like this, and so on and so forth. Okay, so what we see is that digital signal is actually a signals, are signals which have two levels of current, or you can even say voltages, that are actually represented by 0 and 1. And these are termed as digital signal. Now what do we understand by a digital circuit then? So a digital circuit is actually an electronic circuit in which the current or voltage have only two levels. It is either on or off. So this is what we understand by two levels. Okay. Now this particular graph actually is representing nothing but a typical digital signal in which the voltage at any time can be either 0 or 5. Okay. So now with this we will next move on to the logic gates. So let's get started. So logic, a digital. So first we will start with the very definition. So a digital circuit which either allows a signal to pass through or stop it is called a gate. So this is the very definition of gate. Now the gate and logic gate is a little different. So such gates that actually allow the signal to pass through only when some logical conditions are said to be satisfied or are satisfied. So it is a little add-on with regard to gate definition. Then you call it or termed it as logic gates. Now why we are actually learning logic gates? So logic gates are actually the building blocks of digital system, and that is why we require to know it, because we are dealing with electronics. Now each logic gate actually follows a certain logical relationship, and this relationship will be portrayed between input and output voltages. Now basically there are the basic logic gates are of three types, or basically there are three types of logic gates generally which we should study. So there are three types altogether. The first one is OR gate, the second is AND gate, and the last one is NOT gate. Okay. Now each basic logic gate is actually indicated by a symbol of and its function, and is defined either by, so this is how they are indicated and how they are defined. This can be either done using a truth table, or you can even use the Boolean expression. You can use either of the ways, go for either of the ways. Okay. Now in case of digital circuits, we mostly use junction diodes actually, or transistors as switches to change from one voltage level to another. Okay. Now in the analysis of digital circuit, we actually find out that whether a voltage is low or high. Now in the digital circuit, low voltage will be often represented as 0. So this is low. Often, not always, I am not using the term always. And high voltages are often represented as 1. Next we move on to truth table and Boolean expression. So truth table and Boolean expression. So we will first know what do we understand by the two terms. So truth table, so let me change the color. So okay, truth table is a table that actually shows all possible input combinations and the corresponding output combinations for a logic gate. While the Boolean expression, this person, Mr. George, actually invented a kind of algebra. So it's a kind of algebra which actually deals with logical statements that have only two values, namely either a true or a false value. Now the logical statements are called the Boolean variables. Now if I tell you more about the true values and the false value, then the true value of a Boolean variable is actually denoted by 1 and their false value is actually denoted by 0. It is noted that the symbols 1 and 0 have nothing to do with numerical, they have nothing to do with the numerical values 1 and 0. So here in Boolean, for Boolean algebra, if you write 1, that it means that it is true. It is not actual numerical value in the number system which you are using. So it is actually, both are different. Now in case of electronic circuits, the symbol 1 and 0s are used to represent active state and passive state. Now in simpler words, if you want to know, then active state actually mean on state and passive state actually means off situation. Okay, so it is of a circuit component, and this can be anything, a diode or a transistor or a switch, etc. Okay, next we move on to a little more signs with regard to sign that you see here is number 1. In Boolean algebra, the addition symbol that is given by this, so just let me write it. So this is the addition symbol, is referred to as OR, and the Boolean expression is given by a plus b is equal to y. This actually, if this is the thing, so it indicates So in place of y you will replace it by or, so indicates that y equals a or b, but this or means not only this or this, it is means addition of both. Okay, now we will learn a little bit about OR gate also. So the OR gate is a gate that combines A with B, and this is to give Y as a result. Now I'll just reduce the ink size a little bit. The OR gate has two or more inputs, but it will definitely have one output device. Okay, and the logic symbol of OR gate with A and B inputs and Y as output can be given by this particular diagram. Okay, this particular diagram actually shows our OR gate. Now, so this is with regard to the addition symbol. Now we move on to the multiplication symbol. So, number 2, the multiplication sign is either into or is referred to as, this particular multiplication sign is actually referred to as AND in case of Boolean algebra. So the Boolean expression A into Y, so you are multiplying, this is how we give. So it actually indicates, so you replace this dot which actually denotes the multiplication sign by AND, so it equals Y equals A and everything will be in capital B. So this is how you write this. Now next we will move on to AND gate. Now the AND gate, let me reduce the ink size further. Is a device that combines A and B, A with B to actually give Y as a result. Now the AND gate has two or more inputs, as we have discussed in terms of OR gate, and one output device. Now the logical symbol of AND gate, so this is nothing but the AND gate diagram. So the logical symbol of AND gate with A and B as inputs and Y as output can be well portrayed using this figure. Now we move on to we have already discussed two symbols, so we will discuss the third symbol. Now the bar symbol which is actually given by this is actually referred to as NOT. in Boolean algebra. So the Boolean expression a bar equal to y actually indicates y equals not a. Now the bar symbol over a actually means that we change a to the alternative digit since in the binary system 1 and 0 are the only two digits. Therefore we have 1 bar equal to 0 and 0 bar equal to 1. Thus we can say that NOT operation is also called the negation or inversion. Now the NOT gate is actually a device which inverse or not inverse, I shall write, inverts the inputs, isn't it? So if input is 1, the output is not 1 but is 0, and if the input is 0, then output is not 0 but is 1. Now the NOT gate is one input and one output. So this is the input and one output device, and its logical symbol is nothing but this. Next, what we are going to do, we will talk about some useful laws of Boolean algebra. Okay, so let's speak about them. So now we are talking about useful laws of Boolean algebra. So first is our commutative law. So you know this very well. I'm just doing it because we will be requiring it. So A dot B is equal to B dot A. Second, you have associative law. So this is A plus B plus C is equal to A plus B plus C. So you can replace it using dot. So A dot B dot C, A dot B dot C. Third, we have distributive law. So distributive laws, and these are A dot B plus C is equal to A dot B plus A dot C. So you can rewrite this as A plus B dot A plus C is actually equal to A plus B into C. And last one thing I'll talk about, one more. Actually we'll talk about some more. We'll also do the De Morgan. So fourth is our redundance loss. So 1 a plus b, a into b is equal to a into a plus b is equal to a, 0 plus a is equal to a, 2 0 into a is equal to a, this is plus only, 1 plus a is equal to 1, 1 plus a is equal to, this is into, then you have a naught plus a is equal to 1, a bar into a is equal to 0, a plus a bar into b is equal to a plus b, a bracket open a bar plus b is equal to a dot b, a dot a plus b is equal to a dot b. Fifth, we will talk about the double complementary function. Complement functions actually. So a double bar is equal to a. 6 is Boolean identities. So here you have a dot a bar plus b is equal to a dot b. Second is a plus a dot b is equal to a plus b. Third is, if you have a plus b dot c, it will give you a plus b dot a plus c. And 4, a bar plus b dot a plus c gives you a bar dot c plus a dot b. Now we move on to the last one, which is De Morgan theorem. Now it actually states that the complement of the whole sum is actually equal to the product of individual complements and vice versa. That means, if I want to tell you in notation form, it will be a plus b under bar is equal to a bar dot b bar, and a dot b under bar is equal to a bar plus b bar. Okay, now I'll show you one table. This is this particular table which you can see here is called the truth table, and you can use all the identities which I have just said and verify these tables. Okay, now in this particular truth table you can see that column 4 and column 7 are identical. Hence we can say that the theorem stands proof because we have a plus b bar under bar is equal to a bar into b bar. Okay, which we have done under the De Morgan's part. Okay, and the column, so let me pick another color, and the column 9 and 10 are also identical. Hence the theorem stands proof, which is a dot b bar is equal to a bar plus b bar. So De Morgan's also states that, so let me write De Morgan theorem also states that A bar plus B bar under bar is equal to A double bar plus B double bar is equal to A dot B. So this is there, and you also have, I'll mark it as 4. So you have 1, 2, 3, 4. So A dash into B dash under dash is equal to A double dash plus B double dash, and this can be written as A plus B. Now these can be actually proved using this truth table. So we will be actually using the identity here. So what we will do, we'll try and prove one identity. Okay, so we are trying to prove, say this, A plus A bar dot B is equal to A plus B. Now taking left hand side and applying the distributive law, so we have picked the left hand side and we are also applying the distributive law. We get A plus A dash dot B is equal to A plus A dash dot A plus B. This will, the first thing will actually be 1. Okay, we have this, and you keep this as it is. So this can be written as A plus B. And lastly, now before winding up today's tutorial, what I'll do, I'll talk about the basic OR and AND relations. Okay, so I'll just do this and then I'll wind up today's tutorial. So first, this is for OR and this is for AND. So I'll be writing 4. Number 1, A plus 0 will be 0, and this is A dot 0 is equal to 0. Number 2, A plus 1 is equal to 1, and here is A dot 1 is equal to A. Then you have 3, which is A plus A is equal to A. This is A dot A is equal to A. There is no difference. And fourth is A plus A dash is equal to 1, whereas A dot A dash under AND will be equal to actually 0. So this is all basic introduction about the gate, OR and NOT, Boolean algebra, etc. Now in our next class we will talk about realization of OR gate, etc. and this is how we are going to proceed.